Hi, good morning, good afternoon, good evening, everyone, and welcome to our next webinar in a three-part series. This is the Kinetis Flex Your Mind with Kinetis FlexIO. I'm joined here today with Donnie Garcia and Alessandra from Hackster, and today is exciting because we're going to be doing a live hands-on walkthrough of the FRDM-K82F board. So you'll actually get to see kind of in real life how to get started with the development board. Before we get started, I'm going to turn it over to Alessandra for a few words and updates about the contest.
Thank you. Hi, this is Alessandra from Hackster. I'm really excited about this webinar and about the contest. We have over 250 really amazing ideas that have been submitted so far. And I just wanted to let everyone know that we've started picking out the pre-contest winners. We're going to be shipping the boards a little early. So if you're a pre-contest winner, you should have gotten an email from me last night. We haven't announced anything officially on the contest page yet, but we wanted to give everyone their boards so that you guys can start building your projects, and they'll be shipping in the next few days. So thanks again, and Donnie, back to you.
Okay, great. So hello again, everyone. And the goal for today's webinar is to actually go through and show you some examples, loading the examples, using the software, so that way when you do get your board, when you do get your hardware, you begin implementing your idea, you have some reference point. And so before I get started, I just want to recap a couple of things from the previous webinar. So we had our first webinar a couple of weeks ago, and that's where we learned about the problems in embedded design that the FlexIO is designed to address. We learned the details of the FlexIO block itself, the timers, the shifters, the triggers, and how they all work together to transmit and receive data. And we also looked at some of the software that we have in our Kinetis SDK, and we introduced the challenge. And then last week, we actually went a little bit deeper, and we talked about how you get your Kinetis SDK, where the FlexIO signals on the FRDM-K82F reside, and how they can be expanded with expansion boards like the Seed Studio, Expansion Shield, and the Growth Sensor. So, you know, today we really want to focus on the tools and the hardware and show you how to actually use them. So we have a camera set up so we can actually show you some of the FlexIO examples in action. And so we're going to look at the FRDM-K82F and how it works with our IDEs, and we're going to run some examples. So it's going to be switching between a couple of different views here, so you can follow along watching the video feed when I show you some of the hardware and also on the screen. And so if you recall from webinar 2, we gave you some very nice direction on how to get the Kinetis SDK. And this Kinetis SDK will come in a folder. And one of the first places we want you to reference is the documentation related to the Kinetis SDK. And so you can see this is my SDK directory. And in here there's a docs folder. And a very important document is the Getting Started with the Kinetis SDK document. And so if I open this up, there's some great information in here. So in our Kinetis SDK, the software package we deliver with Kinetis MCUs, it can work on different integrated development environments. Depending on your tool chain, there's some explicit directions on how to use the tool chain. And one of the great things about the FRDM board is it's updatable, so that way you can change your environment. And so one of the important sections of this document is Appendix C, updating the OpenSDA firmware. So in today's examples, I'm going to be using the Italic IDE, Italic True Studio for ARM. And one of the prerequisites or the previous steps that needs to be done is to download the appropriate SDA image so that way we can use this tool. And so once you download the Kinetis SDK, you have access to this document, and it gives you some explicit directions on how to do this. And it's pretty straightforward. We have on the board a reset button right here on the left hand side of the board. And you simply hold that reset button down, and while that reset button is pressed, you insert the USB cable into the appropriate USB connector, and then the board will enumerate as a bootloader, and you can update the bootloader that way. And so in order to use some of the tool chains like Untitled Studio that I will be using today and the Kinetis Design Studio, this is a step that needs to be done. And so one of the great examples that we have for the FlexIO and the FRDM-K82F is a web camera. And so I wanted to walk you through how to get this web camera working on the FRDM-K82F board. And so in Untitled Studio, you can come to the File menu and do an import. And in the general heading here, you will see that there's a way to import existing projects into a workspace. And so if you click on that and the next button, and then browse to your Kinetis SDK directory, so here's my Kinetis SDK 2.0 FRDM-K82F directory. There will be a folder for boards and a folder for the FRDM-K82F. And in here, there will be USB examples. And so we really want to highlight this because it's not exactly where you would intuitively think that this example would be. But in the USB examples, you can see we have this USB device, Video FlexIO OV7670. So let's talk a bit about the hardware. The FRDM-K82F comes with a socket where a OV7670 camera module can be placed. And so you can purchase this OV7670 camera module at eBay or Amazon, or just do a web search and you can find it for about $8 or $9. And so this is additional hardware that's needed for this demo. And so here you can see all the different tool chains that are supported in the Kinetis SDK. We have IR, Kinetis Design Studio, and so on. And in this case, we're using a Untitled tool chain. So I'm going to click on the Untitled folder, ATL, and you can see it brings up this demo into this workspace. And so once you have this demonstration in your workspace, you can build the demonstration. This is taking the software that's provided in the Kinetis SDK and generating the output files. And then after that build occurs, you can program the device. And it's important to note a couple of things, that the FRDM-K82F has two different USB connectors. It has a USB for the MCU itself, and this is the USB connector that's in the middle of the board. And it has a USB connector near the reset button for the debug tool that's on the board itself. And so when you program the device, you plug into the USB connector associated with the debug tool. And when you use the video camera, you use the USB connector in the middle. And so once you have built your program, you can choose a debug configuration and select the debug here. And so I've already programmed this board, and just to give you some visual on the camera, you can see this is a nice USB video camera. I'm pointing towards some of the boards here. And besides the capabilities of just getting the data in, this tool, like many other tools, has some other capabilities around streaming the camera data on the website, or a very nice motion detection feature where you can look at and detect motion with this tool. So definitely a nice example that we have in our Kinetis SDK. Just some concepts. There's separate USB connectors for programming the device, then for running the USB demo, and there's separate hardware that can be attached and needs to be obtained to do this demonstration. So very nice tool that we have in the Kinetis SDK. And so I'm going to close that out and focus on another software enablement that we have that is really going to help you with your projects. And so I'm going to import a different project, again by going to the File menu and Import, and then browsing to my Kinetis SDK directories, and the boards and FRDM-K82F. And in here, there's a folder for driver examples. So you see this driver examples folder that I have highlighted here. And specifically, we have a folder just for the FlexIO. And FlexIO has drivers for I2C, for SPI, and UART. So I'm going to click on this I2C. And within this I2C folder, again, we have a project for reading the accelerometer on the FRDM-K82F board itself. The FRDM-K82F board comes with a very capable accelerometer, and we're going to select the Untitled toolchain again and import this project into our workspace here. And so let's take a look at this project, and you can see there's folders for the board, for the documentation, for drivers, and in the documentation folder there's a README. And so if I open up that README, this gives you some ideas of what this project does. And the goals of this project are called out here at the top. It will direct you on how to use the FlexIO I2C master driver, and it will show you how to interface to the accelerometer that's on this board itself. And so there's some board settings, if you see this text that I have highlighted here. And we're gonna do these board settings on this board to run this example. So you can see there's a connection for the I2C pins to go from J12 pin 3 to J12 pin 15 and J12 pin 4 to J12 16. So I have a couple of jumper wires here, and I've modified this board already with a header at the top to easily have jumper wires connected. So this header is labeled, and so if it's maybe a little bit difficult to see, but once you get your hardware, you'll see that the header is labeled with pin 1 and pin 2 and pin 17 and pin 18. So if we want to take this and connect pin 3 to pin 15, it's pretty straightforward. We can go from pin 3 to pin 15 and pin 4 to pin 16. So this is some hardware connection that's necessary to run this demo. And so I have that set there. So let's take a look at what we're actually doing with these hardware connections. And so if I open up the schematic for the FRDM-K82F and go over to J12, J12 is labeled here as the FlexIO/camera header. This is the same place where I had the camera inserted. And what we're actually physically doing, we're making a physical connection between FlexIO pin D5, which is here pin 15, and that's physically being connected to this I2C SCL pin, and FlexIO pin D4 is being connected to the I2C SDA pin. And so these connections are associated with this software that we're going to run on this board. So if I have a look at the software, you can see that we have some defines at the top of this software file for defining SDA pin as associated with FlexIO D4 and SCL pin with FlexIO D5. And so this is tying the hardware configuration and the software together. So I'm going to build up this project and show you how to download it to the Freedom board. So again, 2 USB connectors. One is closer to the reset pin. Because I'm going to program this board, I'm plugging into the USB connector associated with the programming and debugging of the device. And I'm going to select the debug configuration and download this program over to the board. And so it's making a connection, downloading the software, and this software has a debug terminal associated with it. And so I'm going to open up the COM18, which I know is associated with this program at this terminal. And so if I put these two things side by side here, and I run this program, you can see that the FlexIO software that we provide in the Kinetis SDK is interfacing to the sensor. Right now, let's focus on the Z-axis. So the board is upright, so the Z-axis is positive. if I turn the board upside down and rerun this program, you can see that the z-axis is negative. So this is just a simple demonstration of the FlexIO and how it's interfacing to this board. But we wanted to give you some idea of how to expand this, how to utilize all of the FlexIO capabilities. So we're going to go through and build from this example and make some changes in order to do different functions with this I2C example using FlexIO. So in order to do that, let's take a look at the hardware again. And so if we go back to our FRDM-K82F schematic, we can see that the I2C sensor, this FXO S8700 sensor, it is actually connected to pins PTA1 and PTA2. And as I said before, we're using physical connections from some FlexIO pins coming out of the board and going into these PTA1 and PTA2 headers. And so the thing is, FlexIO, we learned in webinar 2 that FlexIO is actually distributed. It's just distributed across the chip, and it's distributed on the board. And so what can we do to reduce the hardware complexity and implement the same demo, but with less hardware? And so if we take a look at the reference manual for the K82, and we look at the actual pins that the sensor is connected to, we know that it's connected to PTA1. And so PTA1, as I have highlighted here on my screen, is actually FlexIO D11. And PTA2, using the reference manual and the pin multiplexing, we know is FlexIO signal D12. So instead of using FlexIO pins D4 and D5 coming out of this header and going into these physical connections, what if we just changed our software to use FlexIO D11 and D12 and in a way simplify this design? And so how can that be done? It's pretty straightforward using this example as a template. So the first thing to do is change these defines here. So right now the SDA pin is defined to be using FlexIO pin D4, and we need to change it to use FlexIO pin 11. And the SCL pin is defined to use FlexIO D12, and so we have to change this define as well. And then after we change these defines, the next step is to update the pin multiplexing. And so if you look at my screen, there's a folder for the board and a C file for pin multiplexing. And in here, we have to associate PTA1 and PTA2 with the right pin multiplexing. And referencing back to the reference manual, let me go there real quick. You can see across the top of this table, we have all the different multiplexing options called Alt0 through Alt7, and FlexIO pins happen to be on the Alt5. And so if we go back to our software, we need to update these pins to use the multiplex Alt5 for both the SCL and SDA pins. And so updating these and then rebuilding, if everything works as expected, we should be able to interface to the board without these physical connections on the board itself. So I'm going to go and reprogram the board. So now I have the jumpers removed, and I can run this demonstration again, and we can see that the sensor is being interfaced to, now instead of going out of the certain FlexIO pins onto others, we've used the chip multiplexing and the software, updated the software with about, changing 4 lines of code, the defines and the pin multiplexing definition. And we can run this demonstration now without the physical connections to the board. And so the main value here is we talk about FlexIO allowing you to reduce time to market. And so whether it be an issue in your schematic design or just constraints in where you can place parts. Having FlexIO distributed across a chip and the ability of the FlexIO to emulate different interfaces is key to enabling you to reduce your time to market. And so this is just one example of being able to do that. So let's have a look closer at what the software is doing in this example. And so I'm going to focus in on this main C file. And we talked about the defines at the top of the board. These are defining which pins, what baud rate is being used, and so on. There's some defines associated with the accelerometer. And then we have a number of functions in this demonstration. We have a callback function to define what gets done when the I2C communication occurs. We have a function related to the accelerometer who am I register. So this is pretty interesting. Some advanced sensors, like the sensor we have on the FRDM-K82F, they have a capability of being addressable at a common I2C address. That way you can discern what the address of that sensor is. And so this function uses the FlexIO I2C emulation and interfacing to the sensor to do that. And then we have a couple of functions for writing the accelerometer registers and reading the accelerometer registers. And then we get into our main file, and this is where we go in and initialize the hardware and the clocking, and we have a command interface to initialize the sensor. So we're sending some data over to the sensor to get it ready to be utilized, and then the main loop is here, where in this function, for a defined number of times, it goes through and waits for the sensor to be ready to be accessed. And then this main command here is reading the accelerometer. So these are the important functions of the device. And one capability it utilizes is the FlexIO I2C master driver. So if I look at our workspace and expand the drivers out, you can see that this FlexIO I2C master.c and master.h, this is actually part of the Kinetis SDK. So this is a generic I2C driver associated with the I2C capabilities of the FlexIO. And so I want to focus in on a initialization function so we can show you how the FlexIO is actually being used. And I'm going to reference webinar 1 because in webinar 1 is where we went through and talked about how to transmit and how to receive information utilizing the FlexIO. And in order to do that, this I2C master driver for the FlexIO, it uses 2 shifters and 2 timers. And here you can see the initialization of the shifter 0, the initialization of the shifter 1, and the same for timer 0 and timer 1. And so in the webinar 1, we went through and talked about how these are set up, but I'm going to give a quick overview now. So both shifter 0 and shifter 1, these are utilizing, being triggered and timed by the timer 1. And you can see that's associated here in this structure for the shifter configuration. In this highlighted piece of code, you can see that the timer index is pointing to timer 1. And for both transmit and receive, the timing of the shifting and the triggering of the shifting is associated with the timer 1. And these 2 shifters, shifter 0 and shifter 1, one is set up for transmit, and you can see that that's highlighted here in this line of code where the shifter mode is set up for transmit, and the other is set up for receive. And then in regards to the timers, timer 0 is used to set up the baud rate and bit timing, and it's configured here in this segment of code, and timer 1 is used for counting the clock cycles. And you can see it's associated with the actual clock pin, the SCL pin, and it's counting how shifting data in and out based on that clock pin. And so we want to build upon this example, and the scenario that we're going to implement is, well, what if we wanted to monitor this I2C data that is going to the sensor? How can we do that? And so I'm going to leverage this driver code that's provided in the Kinetis SDK and bring some of that code over into our project that we have open. And so the first thing is initializing the structures for shifter and timer config. And so I'm going to take these lines of code here, the FlexIO shifter definition of the structure and the timer, and also a very important function of initializing these to 0 to make sure that the data is initialized to a known state. So I'm going to copy these over and bring them into our project and put them over here in our main as local variables that we're using to initialize these shifters. And so once we have that over into this main function, now we can use these structures for shifter config and timer config to build upon this example and do some monitoring of the I2C data. And so again, we're going to monitor the received data. And so as a starting point, we can utilize the initialization of the shifter 1. And so we're going to copy this initialization of the shifter 1 over into our project. So if I come down into our main file and copy this over, we're going to change our comments here. So we show that this is initializing shifter 7 for monitoring I2C data. And we're going to, instead of utilizing some pointers that the generic driver utilizes for interfacing to the FlexIO, we're going to make some direct defines. So when we have this timer select, we're going to utilize timer 1 for now. And then this is pointing to the SDA pin or the data pin, and we already have it defined for this in our project. So I'm going to pull that define from our project. Instead of utilizing this pointer to this SDA pin index, we're going to hard code it to this SDA pin. And then we also have some pointers in this driver for different identifiers here in this shifter config call. And so we know we're using FlexIO 0. This is the peripheral that we're utilizing. And in terms of the shifter, we're initializing shifter 7. And so this allows us to utilize local defines instead of the pointers for this shifter config. And so for shifter 7, we want to bring the data in and be able to monitor it. So it's configured very much like the shifter 1. It's being clocked by the timer 1. It's monitoring the SDA pin. But the great thing about the FlexIO is that it actually has more resources. And so the way shifter 1 is configured now, it's bringing in data 1 byte at a time. But for this demonstration, we want to bring in a whole string of data, all the data that we're getting from the I2C sensor. So instead of just initializing the shifter 7, I want to go on and initialize other shifters. And so I'm going to add these lines of code here to initialize shifter 6 through 2 for monitoring I2C data. And if you remember from webinar 1, we can link shifters together. So as data gets shifted into shifter 7, we can link these together, and the way that is done is by setting the input source of the shifter. And so this is a very nice way to utilize the environments and the drivers. So if you highlight this definition for the shifter input pin and say open declaration, you can see all of the options here in this enumeration. And so if we want to pick up data from a previous shifter, instead of shifting in data in from a pin, we can shift data from a shifter output. And so I'm just going to copy this definition and come back to our firmware here and paste this here. And so now this configuration is set up so that as the data comes in, the data gets shifted into the pin 6, the shifter 6. And so we want to update the shifter config so it utilizes the shifter 6. But we also have more resources than shifter 6. So we can go through and associate that same initialization with the other shifters. So shifter 5, 4, 3, and 2. Remember, shifter 1 and 0 are already being utilized by the icrc driver, and so we cannot use those. But once we've updated the way that the data is being brought in, we can link data first comes in through shifter 7 from the pin itself because it's set up in receive mode. This command here is setting it up for receive mode. And then we can bring that data in from the next shifter with this input source and associate that with all of these signals. So the other updates we need to make are, right now the demonstration is set up in order to bring in data just 1 byte at a time, and that's because it's associated with the timer 1. But we want to bring in all the data that we're receiving. If you remember the demonstration, we're looking at X, Y, and Z, and all of these byte transfers add up to a lot more data than just 1 byte. And the way we're going to be able to do that is by updating the timer associated with these shifters. So again, I'm going to leverage some of the firmware that's already there for the timer 1 configuration. So timer 1 is set up to control the shifters, and I'm going to copy this configuration over into our main project. And so let's change our comments because this is we're going to initialize the timer 2. Bring in multiple bytes of data. So the trigger will still be the shifter 0, but again, we need to align to the local definitions. And so I'm just going to hard code that to shifter 0 instead of using a pointer. The pin, again, will be the SCL pin. And we have a define for the SCL pin already done here at the top of the project. And so I'm going to update that line of code as well. And then we need to make a couple more changes because right now it is set up to do 1 byte transfer at a time. And we want to bring in many bytes. And so in order to do that, we need to update the firmware so that way the timers is not disabled. So again, a very nice way to use our firmware is to follow the declarations associated with different defines. So if I open this declaration, I can see that here are all the options for setting up the timer. It can be set to disable never, and that's the option that I want to utilize. And then the rest of these parameters, they can remain the same, but we want to make sure that the timer is reset never and disable never. And the enable of the timer, it needs to always be enabled as well because we're looking at stream of data rather than sending in or sending out a defined protocol. And so I'm going to again go to this declaration and use this timer enabled always. And so icrc, it's a pretty complicated protocol in that it has start and stop bits and repeated starts and so on. So it's a little bit difficult to define how many bit shifts are needed to look at relevant data. But I know from previous working on this project that if we shift in 161 times the falling and rising edge of the clock, then we'll get in the relevant data for the accelerometer. And so I'm going to set that timer compare value there. And then again, I pulled this code from a driver that is using pointers to make it more dynamic. But inside our main function, we're going to define hard code the address, the exact FlexIO peripheral we're using, the timer that we're configuring, and this will allow us to localize this function. And so now instead of using the timer 1, these shifters that we're setting up to monitor data, they're going to use the timer 2. So I have to go back here to the timer select and make sure they're associated with the appropriate timer. And so there's a great deal of communication going on during this process. And so the proper place to turn on this icrc monitoring needs to be defined. And so we don't necessarily want to monitor the polling of the accelerometer status. We really only want to monitor once the icrc accelerometer is being read. We want to monitor only the relevant data. And so in order to do that, I'm going to move this code to initialize the timer 2 and turn it on. I'm going to move it to right before we go off and read the accelerometer. And so I also need to, because this function is looping multiple times, I also need to initialize the timer in order to set that timer to a known state before it gets reset here. So I'm just going to set the timer control value to 0. This will reset the timer, and then this line of code will go off and I'll actually configure the timer to monitor the icrc signal. So a lot of lines of code added there. So I'm going to build this, and we're going to see if this will work out. Okay, so I have a improper call here to the timer control. So let me see. Timer control. So I'm going to cheat a bit here. I have a previous implementation, so I'm just going to bring that up to see the syntax that I'm getting wrong here. Let's see, bear with me here. So this is the proper syntax I was going for. Let me rebuild that. So we're going to run this demonstration and see if we can monitor the icrc signals now. So a very nice feature inside the Atomic debugger is this access to all the registers. And if I come down here near the bottom of the peripheral registers, we'll find the FlexIO, and we can see that all the FlexIO signals are highlighted here. And the relevant data or the relevant registers that we want to look at for pulling in this icrc data are the buffer registers. And one interesting thing that we haven't reviewed before is all of these buffer registers are mirrored in different ways. There's aliases to do bit swapped, byte swapped views, bit and byte swapped, and nibble byte swapped. So when you're shifting in and shifting out data, it's not necessarily always coming in the right format. And so we have these different views of the data inside by these alias registers. So I just ran the demonstration before I set a breakpoint. So, but you can see here that these relevant registers, buffer 7 through and 6 and 5, these are all getting loaded up with data. And this is the icrc data that is coming through. And so I'm going to actually put a breakpoint here, toggle a breakpoint, right before we, right after we read the icrc data and rerun this. And so that way we can see this data changing dynamically. And so if I turn this board upside down and rerun this, okay, so what we're trying to show here is that a couple of things. We have this read buffer that is already part of the demonstration, where we have the code coming in and being analyzed by and output into the COM terminal. And we also have the registers where the data is being shifted in. So it seems like our demonstration is getting hung up somewhere. So I'm going to try and debug this a bit. So bear with me here. So I'm going to run this demonstration again, and it's getting hung up right after. Okay, so it is working here, and so what we really want to get at is show that this information is being updated into these buffers, and we were able to do that with the FlexIO by updating the shifters to shift in this data. And so I'm having a bit of a difficulty demonstrating this data showing changing dynamically. So let me pause here and try and debug this a bit. So let's see. Well, in the interest of time, I'm going to go ahead and copy over the previously built project. It could be something really straightforward or simple there, but in the interest of time, I want to get to the crux of the demonstration, which is what the FlexIO can do here with monitoring the data. So I'm going to rebuild this project and rerun this demonstration, if you bear with me. So one of the things we want to show is the association of the data in the FlexIO itself. If we look at this data here, we have the data coming in. It's being highlighted because it's changing dynamically. And what we have set up on shifter buffer 7 is a data match. And so in this data match, you'll see shifter buffer 7 does not change because it's set up for a match until that match value is achieved. And so if I turn the board upside down, this match is set up to detect when the board is upside down. And when I run this demonstration again, you'll see that the match value can occur, and the data does get updated here dynamically on the match. And so having a bit of a difficulty here, but the main concepts are that the shifters, they can be updated with the leveraging the driver code that is in the Kinetis SDK. And then once the shifters, the shifters get the data in, they can be updated so that way they can be implement a match store mode. And so that's what this line of code does here. And then once that match store mode is configured, we can use another FlexIO resource for setting an LED alarm. And so what the demonstration is really supposed to show, let me try just simply rebooting it here. What it's really supposed to show is as the board tilts upside down, it should drive a LED. And I think that I just answered my own question here in that the reason why it's not working is there's some hardware configuration that I skipped. And so just to try and catch that quickly, the in demo uses the RGB LED. And so if I come over here to our hardware, our schematic, and come up here to the RGB LED in our schematic and zoom in on this, you can see that there's PTC9 is associated with the green LED, and a step I skipped in my haste is setting up the pin muxing for PTC9. And so we have already some pin muxing set for port C, and so I'm just going to add a line of code here to update the pin muxing for PTC9. And so put 9 there, and I know that the FlexIO is associated with mux 7. And so this is actually enabling the FlexIO function on the PTC9. And so now I have to rebuild this and program the board again. But what the purpose of this example was a couple of things: is show that how to leverage our SDK, how to see all the different options for defines, and then how to grow upon an already provided example, add some buffers, and also make an alarm. So let's try this one more time before we pause for your questions. So I'm going to program the board. And run this demo. And so now if I tilt the board over, you can see that as long as the board is upright, the alarm LED does not go off. But as I tilt the board down, the alarm LED there goes off because the FlexIO is monitoring the data as it's being shifted in. Specifically, we're looking at the z-axis and monitoring whether or not that z-axis is reaching a certain threshold. So let me end with a couple of references to the lines of code, the relevant lines of code. And so very important line of code is changing the shifter mode for shifter 7 to match store mode. And so again, you can open the declaration and see that as an option. And then setting up the shifter buffer with a mask and a value. So all the upper 16 bits, these are mask bits. And so you can see I'm using a mask to only look at the MSB bits of the lower byte in this word. And I'm setting a value of C0 for this lower word, which is a strong negative acceleration value. And then some other configuration that we haven't gone over yet is the timer that's generating the LED alarm. And so this is associated with shifter 7. So you can see here that shifter 7 will be the trigger to this timer. It's outputting to a pin. So it's setting up a pin as an output and outputting to the pin 17. And then it's generating a PWM with a very low duty cycle where the upper word defines the period and the lower byte defines the duty cycle for this PWM. And so that's what gets output to the LED to trigger this alarm. So a lot of steps there, and it didn't go exactly as planned, but hopefully you get some idea of how to use the tools, how to download software to the board, and the I2C driver. There's also SPI and UART drivers there as well, and the structures and interfaces that you can leverage in order to use those drivers. So I hope you were able to get some great information there. And before we end that, at the top of the hour, I'm just going to pause and see if there are any questions as we went through all that.
Thanks, Donnie. I do see a couple questions online. The first one is, what are the pins of I2C which I can use to connect to our other hardware to the board?
Okay, great question. And so you can see I have some other hardware here, and one of the other examples that we talked about is using the Seed Studio expansion boards. And the pins, if you look to the webinar 2, we have some nice graphics that show all the pins that the FlexIO goes to. And the advantage of the FlexIO is, even though it doesn't, it may not go to a defined I2C pin in the Arduino form factor, you can leverage other connectors, other places, and connect the I2C. In this example that I went over, I will point you to the exact pins. So what the exact pins have to do with the hardware that's on the Freedom board itself. And that hardware is this accelerometer. And this accelerometer is connected to PTA1 and PTA2. And then if you recall, we looked at the reference manual to look at how PTA1 and PTA2 are defined. And you can see that those are FlexIO pins. So anywhere that FlexIO goes, those pins can be I2C pins. They don't even necessarily have to be pins that are side by side. If you wanted to use different FlexIO pins that are not side by side, you could do that. And I showed how you can update these defines here at the top of this example. In order to do that, it just so happened we use FlexIO pins that are side by side, but they can be separate pins. There is a requirement that the timers use when you're using the I2C driver, that the timers be side by side, but it can be timer 0 and 1, or 1 and 2, or 2 and 3. So you have some flexibility there in which timers you can use. But in this I2C driver, it depends on the timers being side by side, but the pins can be in different places. So I think that should answer that question. It's in this specific case, in this example, it was PTA1 and PTA2. In other examples that we will be posting, we leveraged Arduino form factor D4, D3, D6, and D7, and specifically D6 and D7 as I2C pins. And if we open up the schematic again for the Freedom board, you can see these are the specific pins that we use in this expansion example that we're going to be posting. They're PTC10 and PTC8 and PTC9, so D6 and D7 were used as I2C pins in this example.
Great, thank you, Donnie. The next question, apart from a software from Untitled Chapter for ARM, can I use any other software like Kyle or icrc or anything else?
Yeah, so we have support for the Kyle tools as well. So let me open up the SDK and an example project. So if I open up the USB examples again and go to the camera example, you can see we have MDK, KDS, which is Kinetis Design Studio, IAR, Atolic, and ARM GCC. So all of these are part of the Kinetis SDK for KD2. And I didn't realize the timing of that it would take. I was going to utilize another tool chain and show another example for expanding through the Seed Studio board, but we're a little short on time. But just to emphasize this, we're going to post a walkthrough of this expansion that we're working on onto the site to show, you know, there's some steps. You can leverage the header files and the C files associated with this sensor board, this growth sensor, and also this example that I went over, the I2C read accelerometer example, and build a nice demonstration of using these touch sensors. And just to emphasize some of the value of the FlexIO, so sensors, they're pretty smart. They can tell you when any of these touch pads are being touched, it can tell you that. But if you want to know when a sequence is occurring, if you want to know only when all four are being touched and they're being touched for a certain amount of time or a certain amount of samples, that's where the FlexIO can really help you make your sensor smarter in that it can, using some of the same strategies that I overviewed today, by monitoring the I2C data and setting alarms and matches, you can not only know when any touchpad is being touched, but know only when all four are being touched, or two of the four, or three of the four, and then also know that it's been touched a certain amount of times. And that's this example we're going to be posting that I was going to try and show today, but we're already at the hour there. So, any other questions?
Donnie, there's actually a number of questions, so I think we'll need to follow up via email for the rest of the questions that we've seen, and we'll do so today. Meanwhile, thank you so much for doing this live demonstration. I know it's always stressful because things can go wrong when we're doing things live, but I'm sure people will appreciate it even more when they receive their boards and are working on their own design to reference this recording and walk through the step-by-steps as they get their board. As a reminder, all the examples that Donnie mentioned, the webinars, the recordings, the slides, everything we keep posted to the contest page. And Donnie, do you have any closing remarks?
No, it's really exciting to see all the ideas like was already mentioned, and we hope that you know, you can make your ideas a reality, and we're looking forward to this contest and the prizes and so on. So very exciting. Thanks for all your submissions so far, and I hope you're new to the contest that you have some idea that you post and you know, really use this exciting peripheral we have on Kinetis MCUs.
Great, thanks, Donnie. To our attendees, everyone, have a great day.
Thank you.